The fact that confined objects such as a neutron in a nucleus or an electron in the atom can only attain discrete energy states cannot be explained with classical physics. A completely new theory had to be developed based on the Schrodinger equation that allowed this effect to be explained. The theory is called quantum mechanics, and apart from Erwin Schrödinger, after which its most important postulate is named, Werner Heisenberg contributed largely to its development. Quantum mechanics is a new foundation of mechanics and includes the classical Newton mechanics as a special case for macroscopic objects. Whereas classical mechanics predicts continuous energy states for confined particles, the fact that these states are indeed discrete, quantized, is a natural consequence of quantum mechanics. Schrödinger developed quantum mechanics as a wave theory and published his work in December 1926. The title of his paper is shown at the bottom here. It was published in the Physical Review under the title An Undulatory Theory of the Mechanics of Atoms and Molecules. At the bottom, the Schrödinger equation is given in its stationary form as it appears in the paper. Apart from the energy E and the mass m of a particle and the potential that represents the forces acting on this particle, the Schrödinger equation contains in particular the wave function psi, which is a new concept that was introduced with quantum mechanics. Furthermore, it contains Planck's constant h, which is the most important natural constant of the microscopic world. Heisenberg developed the same theory using matrix formalisms. Later on, it was shown that both approaches, the wave theory of Schrödinger and the matrix theory of Heisenberg, are equivalent representation of quantum mechanics. The effects of particle confinement are not limited to nuclei and atoms. The photo shows solutions that contain nanoparticles of cadmium selenide that have different sizes. In those nanoparticles, electrons are confined, and if excited, they luminesce in different colors. The example shows that the confinement of particles results in energy quantization. The nanoparticles are such that they have a core shown in red and a shell of atoms surrounding it. The electrons are inside this shell. The diameter of these nanoparticles can be varied. It can be as large as 6 nanometers and as small as 2 nanometers. On the right, the electronic band structure of bulk cadmium selenide and of cadmium selenide nanoparticles is shown. The band gap between the valence band and the conduction band for bulk material corresponds to an emission wavelength that is in the deep red. In contrast, for the nanoparticles, the emission wavelength depends on the size of the particle. A larger particle with 6 nanometer diameter has emission in the red, whereas the smaller nanoparticles with diameters of 2 nanometers emit light that is in the blue visible range. It is clear that for the confined electrons, the spectrum of available energy states depends on the diameter of their confinement. This view graph shows micrographs of nanoparticles. At the top left, many such particles are visible. In the larger magnification view in the corner, a single particle is shown where individual atoms can be identified. It is clear that the diameter of this particle is not much larger than 5 nanometers. At the bottom right, a nanoparticle at the surface of a material is shown. This is known as a quantum dot. A quantum dot also confines electrons in space, causing the quantization of their energy states. The discrete nature and quantization of energy states and their separation become significant when the confinement is such that the dimensions are 10 nanometers or less. If the confinement is less severe, the quantization of energy states still happens. However, they are so closely spaced that they appear as a continuum. The energy quantization, the fact that particles can only adopt discrete states and not a continuum, has important consequences. A really important consequence for us, for our existence, is the so-called triple alpha state at 7.65 MeV in carbon-12. In this case, it's the confinement of protons and neutrons in carbon-12 that causes the discrete nature of the energy spectrum. The 7.65 MeV state is the only stepping stone that permits the formation of heavier elements than the helium that was formed in Big Bang nucleosynthesis. Without this state, the world would consist of hydrogen, helium, and a little bit of lithium and beryllium. For carbon-12 to be created, a very unlikely scenario has to occur. First, two helium-4 nuclei, two alpha particles, have to form beryllium-8, which has an extremely short half-life. During this brief time of about 10 to the minus 16 seconds, a third alpha particle has to be captured so that a resonance state can be formed that is at 7.65 MeV. This state can then decay into the ground state of carbon-12, which is stable and can be the building block for the formation of heavier nuclei via fusion reactions. Since the scenario of combining three alpha particles together is already very unlikely, this situation is only helped by the fact that the 7.65 MeV state is just in the right place, that they can transition into a resonance of carbon-12 that then decays to its ground state. If this state was high in energy or somewhat lower in energy, this transition could not occur. It is remarkable that the complexity of the world as we know it is only possible because of one particular state in the nucleus carbon-12. Newton's laws are postulated and they form the basis of classical mechanics. One important postulate of quantum mechanics is the Schrodinger equation. It is accepted without any proof. It could be contradicted, however, as far as we know, the Schrodinger equation is consistent with all experimental evidence we have, as long as the system is non-relativistic. As Newton's second law, it is a differential equation. Shown here is the one-dimensional stationary form. This means the time dependence has deliberately been left out to improve clarity. It is common to use the symbol h bar, which is equal to Planck's constant divided by 2 pi. The mass m is the mass of the particle that is being considered, for example an electron in an atom or a neutron in a nucleus. The time development of the system is described by the wave function. The wave function psi is a completely new physical quantity. It contains information on the position and the momentum of the particle. Importantly, and this is in great contrast to classical mechanics, the wave function psi cannot be measured. It is a physical quantity which is real, but it cannot be measured. However, not all is lost, because with the help of the wave function psi, expectation values, average outcomes for the measurement of a particular system, can be predicted. The approach of quantum mechanics in solving a particular physics problem can be well illustrated by looking at the solution of the Schrodinger equation for a neutron inside the nucleus. In this case, the neutron is considered a particle in a one-dimensional box with infinite potential walls, confining it inside this square well, and solving the Schrodinger equation for this type of potential. The situation is sketched here. 4 of the nucleons of helium-5, 2 protons and 2 neutrons, form a deep potential well due to their attractive nuclear force that keeps the third neutron inside the nucleus. In other words, the core of 4 nucleons attracts the 5th nucleon. Due to the short range of the nuclear force, the strong attraction is limited to a distance of about 4 femtometers. If the neutron can overcome this strong attraction, it is free and it leaves the potential well. However, the energy required to achieve that is rather large. Therefore, the two potential well on this one-dimensional representation of the problem may be imagined to be infinitely high. As in the solution of any type of quantum mechanics problem, the starting point is the postulated Schrodinger equation. It is adapted to represent this particular problem. Since the potential at the bottom of the well is constant, it may well be set to 0. So we say U inside the well is 0. That simplifies the Schrodinger equation because the second term drops out. The equation can be simplified further by compiling the constants h bar and the mass m into a constant k as the square root of 2me divided by h bar. Substituting this equation star into the Schrodinger equation now turns it into a simple differential equation of second order. Leaving physics for a moment and looking at this differential equation mathematically, we see that it is a familiar differential equation of the type f prime prime equals a constant times the function itself. And we know that the solutions of such differential equations are sine and cosine functions. The most general mathematical solution is given by psi of x is equal to a parameter a times the sine function of kx, whereby k is the k as defined in star, plus parameter b times cosine of kx. Mathematically, we can detail the solution no further unless we have more information about the problem. Such information exists because we can consider what happens at the wall of the potential well. Looking at the sketch, it is clear that the neutron cannot overcome the potential walls because we imagine them to be infinitely high. It is confined to within these two walls. Let us look at this quantum mechanically. The sketch at the top shows the potential with the general solution of the Schrodinger equation superimposed. It is an undulatory function that extends from minus infinity to plus infinity. How does it need to be modified to represent the situation of the neutron at the infinite potential walls correctly? Since the wave function cannot be directly measured, its interpretation was one of the big challenges in the development of quantum mechanics in the 1920s. Ultimately, the so-called Copenhagen interpretation succeeded in giving physical sense to the mathematical solutions of the Schrodinger equation. In this approach, the modulus square of the wave function is defined as a probability density. The probability density psi square is therefore always positive and can be seen as a measure of the likely positions of finding the particle, in this case the neutron. Since the probability density only gives a statistical likelihood for finding a particle, it is immediately clear that the actual position of a particle cannot be predicted with certainty. This is a huge deviation from the ideas of classical mechanics, where both position and momentum of a particle are always known. Applying the Copenhagen interpretation to our particular problem, we have to require that the particle cannot be in the wall, outside the well. This means the probability density has to be 0 outside the well, and therefore also the wave function has to be 0. This provides us with a useful boundary condition. Applying the boundary condition psi equals 0 at 0 to our general solution of this particular problem, namely a sine kx plus b cosine kx, we find that this solution can only be true if the parameter b is always 0, since at x equals 0 the cosine function is 1, and would give a finite result for psi, which would be in violation of the physically required boundary condition. Therefore, the solution of the problem is psi equals a times sine function of kx. In order to achieve this, we have placed the left infinite wall at the origin of the x-axis. We thus have exhausted one of the boundary conditions. We can also take advantage of the boundary condition at the second wall, the right wall, which is located at position x equals L. Again, we require that the wave function at L becomes 0. This can be achieved if the solutions are standing waves with the condition KL is equal to n times pi. The parameter n equals integers that run from 1 to infinity. It is instructive to pause because this is the exact moment where the quantization enters the picture of quantum mechanics. N cannot have continuous real values, but it is an integer. This is required so that the solution of the Schrodinger equation becomes 0, the wave function becomes 0 at the right infinite well. Rearranging and substituting for k, we obtain the complete solution of this problem as psi equal parameter a times the sine function of the argument n pi divided by L, which is the width of the well, times x. Since the modulus square of the wave function represents the probability of finding the particle at a position x, the integral from minus infinity to plus infinity over the probability density has to equal 1, because we know that the particle is somewhere in space. In particular, we know it's inside the well. So therefore, the combined probability has to be unity. Although this is not shown here, it can be derived that the free parameter a therefore has to be equal to the square root of 2 on L. Let us interpret this result. In particular, we want to know what the energies are. Taking advantage of expression star from the previous view graph, we can determine that the discrete energy levels En are given by Planck's constant squared divided by a times the particle mass times the width of the well squared, and this fraction is timed by the quantum number n squared. It is apparent that the integer nature of n causes the quantizations of the energies. The energies are discrete and quantized, as it is observed in measurement. Although we have described the system here only in one dimension, we have in principle achieved agreement with experiment, a great advancement beyond classical mechanics, which predicts that the energies are continuous inside the well. At the bottom left, the potential well is shown again, including the energy states E1, E2, E3, and E4, labeled with their quantum numbers n equals 1, 2, 3, and 4, and because of the quadratic dependence on the quantum number n, they are not equally spaced, but the separation increases with n increasing. For each energy level, the wave function is shown as a dashed curve. For n equals 1, the wave function has no node inside the well. However, that changes as n increases. For n equals 2, there is a node in the center. For n equals 3, there are 2 nodes inside the well. In all cases, as required by the boundary condition, the wave function is exactly 0 at the boundary. The respective probability densities are also shown. Psi squared is shown as shaded functions. As expected, these functions are positive and show characteristic nodes that increase with the quantum number n. Including the nodes at either end of the function and the boundaries, the number of nodes is always equal to n plus 1. So for n equals 2, we have nodes on the boundaries and a node in the center. This has important consequences, namely that the particle, the neutron, can never be found at the boundaries, because at the boundaries the probability density is 0, which is indicative of the likelihood of finding the particle. Furthermore, for quantum numbers with n equals 2 or larger, the particle can also not be found at certain positions in the center of the quantum well, which again is a very different situation as predicted by classical mechanics. For n equals 2, right in the center of the well, the probability density is 0 and we cannot expect to find the particle there. In the case of n equals 3, there are two such positions at roughly 1/3 and 2/3 of the length of the width of the well, where the particle cannot be found. In between these nodes, the neutron can be found with finite probability. In three-dimensional interpretations, these bumps are referred to as orbitals, and the particle is considered to be present in these orbitals with a finite probability. This view graph shows on the right the actual measured energy levels for helium-5. The simplified one-dimensional model of helium-5 that we discussed cannot predict that level scheme in detail. However, it is remarkable that at least in principle, the structure of the energy scheme of helium-5 is given correctly. Furthermore, the wave functions and probability densities associated with each energy level give us insight into nuclear structure. Indeed, our simplified model preempts the nuclear shell model that was developed in the 1940s.